Okay, now in this video, I'm going to talk about the properties of the mixture. So we are still in chapter 13 of the textbook, and I'm going to talk about the properties of the mixture. By saying the properties, I simply mean, for instance, what is the equation for the internal energy? What is the equation for enthalpy, entropy, and the other properties for the mixture? So let's say the capital U, which is the internal energy uh, for the mixture, is going to be the sum of internal energy for each of the component that we have in the mixture. All right. If we have two gases, and if we are mixing two gases, two components, then the internal energy of the mixture is equal to the internal energy of the first gas plus the second gas. Okay, and because this is in caps, because this U is in uppercase, then the unit is just kilojoule, let's say. Now, I can also write that based on the mass of each component multiplied by the specific internal energy of each component. So this is, let's say the unit here is kilogram and the unit here is kilojoule per kilogram. All right, and at the end we end up with the unit of uppercase U. Now in case if I am working with the number of moles, then the internal energy of the mixture is sum of the product of the number of moles in each component and its specific energy. So this Ni is the number of moles, and this U by R is specific energy, and here the unit is, for instance, kilojoule per kilomole. Okay, so whenever we have that bar, the unit is in kilomole. That's per mole. Okay, and this N is number of moles, let's say, or number of kilomoles, I should say. Okay, now we have exactly the same concept here for other properties. For instance, if we are looking for the enthalpy of the mixture, I can say that it is sigma capital HI, which is equal to mass of each component multiplied by the specific enthalpy, and is equal to the sum of number of moles in each component and H bar I. Okay, I can do the same thing for entropy. So this S is entropy, which is equal to the entropy of each of the component, which is equal to product of MISI. So this is uppercase S and this is lowercase s. Okay, so uppercase, lowercase, which is also equal to number of moles for each component multiplied by S by R, S by I. Okay, now these were in caps, these properties were in caps. I can write also in lowercase. For instance, the specific internal energy for the mixture is sum of mass fraction this time. Instead of M, we have MF or mass fraction. This I is supposed to be the subscript multiplied by UI. Okay, so that gives me the specific internal energy. So let me just correct this I here. Mass fraction of component I multiplied by the internal energy. And also I can do the same thing for other properties. So the same concept just applies to H and also S. Now finally, if I'm looking for the specific heat for the mixture, so let's say CV, specific heat at constant volume for the mixture is equal to the sum of mass fraction of each component multiplied by the specific heat of each component. And likewise, a specific heat at constant pressure for the mixture is sum of mass fraction of each component multiplied by a specific heat at constant pressure of each component. In next video, we are going to utilize these correlations to solve a problem.